much more concisely. Oh, and welcome, Taylor. At the very second I started recording, so because I'd forgotten to start recording earlier, but I have to kind of sort of repeat myself anyway. Well, not really. The information's all here. This is everything I've talked about so far today. Is the actual timing of the midterm. So you have the time period there. Be sure to take a look at practice midterm and solution. And that's what I'm going to be going through, as well as just any general tips I might have. Okay, and just as a reminder, chapter 3 material. Okay. As far as actual stuff to cover today, that it's not going to be in the midterm. A very different type of method for solving AX equals B. So we're still dealing with AX equals B in the case where what is going on the screen? Oh man. I hope it keeps up when I scroll. Oh, yeah, there's a bit of a delay here. I guess because of probably because of a shoddy internet connection. Apparently, Wi-Fi is still on the fritz. Okay, so I'm going to try to scroll ahead so that the account for the delay. Okay. Okay, so we're still trying to solve a problem AX equals B where A is a square invertible matrix. The methods that we saw last time, or not last time, all semester long, chapter 3, called direct methods. So anything that's a Gaussian elimination, would also include, for example, Cholesky decomposition or LDLT. Those kind of factorization-based methods, those are called direct methods. So you just grind through this well-defined finite sequence of steps, and there you have your computed solution. As opposed to iterative methods. So iterative methods are ones that generate a sequence of approximation solutions, and hopefully that sequence will converge to the exact solution. So the first one to establish the need for any alternative to direct methods. So even though we spend a lot of time on direct methods, and direct methods are used all over the place, there's some significant drawbacks to that. That lead us to consider something else that's an iterative method. So here are all the reasons, well, not all reasons, but several significant reasons why using Gaussian elimination-like methods for AX equals B is actually terrible. So for example, you might already have an idea as to what solution should be. Maybe you have what would serve as a good initial guess based on whatever the background information you have about the problem you're trying to solve. And an example of that is something we'll learn about later. If you're solving a system of ordinary differential equations and using an implicit time-stepping method, which would require you to solve a system of equations. So in that case, if you're stepping in time, your solution at the current time is a good approximation already of the solution for the next time. In other words, the solution of your system of equations. So you have an initial guess that's naturally built in. But Gaussian elimination, the direct methods like that have no way, no mechanism for taking into account any information you might have about a approximate solution. So you go to Gaussian elimination like, hey, I already know what the solution is. And they're like, no, we don't care. It's just going to do its thing. So if we have a good approximation, that ought to be a way to save some time. But you can't do that with a direct method. Okay, so that's one big issue. Another big issue is, for a lot of problems, there's no point in getting a highly accurate approximation. Suppose your system of equations, your A and your B, maybe those entries were obtained by measurements. The measurements have error in them. What if you knew that the entries of your A and B were at most accurate to like 1%? Then do you really need to solve a system of equations to 15 decimal places of accuracy? When if there's a way to do less work and settle for less accuracy because that's all you can expect anyway. Again, the direct method has no mechanism for stopping early. It's just going to go through the whole process and get you a hopefully a highly accurate solution to the problem that's presented to it. Whereas if we have an iterative method that we have a sequence of approximations that are getting closer and closer to the exact solution, then in that case, we could just cut off the iterations sooner than we might otherwise. Yes, we are settling for less accuracy, but maybe we're okay with that. And a lot of times we are okay with that in like real world applications, where the mathematical models that you start with are already contaminated with significant error. This is one issue that came up when talking about banded matrices. The matrix is sparse. By sparse, I mean mostly zero entries, such as a tri-diagonal matrix. So using Gauss elimination with pivoting can destroy sparsity. It can introduce many new non-zero entries. That phenomenon I mentioned when I covered banded matrices is called fill-in. So that's another reason for these kind of matrices not to use a method like Gauss elimination. And then finally, you might not even have A as an ordinary matrix, where you have like elements A, I, J. Instead, the matrix A might be represented by a function. So a function takes as input a vector x, and then the output is a product, A times x. So A might only be represented implicitly through a function instead of the conventional like two-dimensional array storage. Now, if all you have is a function, okay, can anyone tell me, if this is all you have, a function that computes A times x for any given vector x, can anyone tell me how you can use a function like this to get the actual entries of A?
Inverse.
We're not talking about the inverse, we're talking about just A. Essentially, it's both on it simultaneously.
Can you repeat the question?
Okay, so suppose I want all the entries of A, but all I have is this function. How can I use this function to still get all the entries of A?
Dealt with situations where we don't have a matrix, but we have a function representing, like a function of some value being a matrix.
I looked into things like that. Yeah, where there is a matrix like product going on, but I never actually say, I don't go to valid and say, here's a matrix. For example, a finite difference matrix, where you're just taking whatever vector comes in and you're working with that. What you can do is you can call this function where x is a column of identity. So if I pass the jth column of identity to my function A of x, that will give me column J of the matrix. And if I do that for all the columns of identity, then I have a whole matrix. But that's a lot of work. We don't necessarily want to do that, especially if A is a large matrix. So, but the point is, Gauss elimination and those kind of methods, or Cholesky computation, they work with individual entries in a matrix. You need to have all of them conveniently accessible in memory to carry out those algorithms. But there are methods for solving x equals b that can work solely with a function like this, and never actually construct A at the ij level. So you think it's like some black box. You don't care how it computes that product, you just know that it does. So here, now, I mean, I don't want to knock direct methods too much. Direct methods are still crucial. In fact, direct methods are used in some iterative methods as like building blocks. But and, but iterative methods also play a pivotal role, especially for certain applications of importance, like solving systems of ODEs or PDEs numerically. Iterative methods are used all the time. I'll bet that if Wilkinson's round-off error analysis of Gauss elimination had returned a negative result, that if it was somehow concluded that Gauss elimination is numerically unstable, then we'd probably be using only iterative methods. Okay, now, in this class, I'm only going to focus on one type of iterative method. These right here, stationary iterative methods. There's also non-stationary. So what we see in this class is in section 5.1, that's on stationary. The rest of the chapter, so 5.2 and 5.3, we don't cover in this class, but it is covered in 6.10. Those are the cooler iterative methods, subspace methods, Lanshos, concrete gradient, all that fun stuff. So we'll see you guys take that class. Okay. So what do I mean by a stationary iterative method? It's an iterative method that can easily be expressed in this form, where you so you come up with some initial guess that I'll call x naught. So look at the notation here. When I have a superscript in parentheses, that's an index of an iteration. So x superscript 0 parentheses, that's the initial guess, and then I'll compute x1, x2, x3. Again, subscripts in parentheses. So what I do is I take my initial guess, I substitute it into some function g, and then I get x1. Then I substitute x1 and I get x2, and substitute x2 and I get x3. Keep carrying on this successive substitution in the hope that these x's will converge to the exact solution of ax equals b. Now, this sort of thing has come up before. In the last semester's class, the 46560, one of the methods we saw for finding a root of a scalar value function of one variable is fixed point iteration. So we were interested back then in solving x equals g of x, so a single variable function. But now we're trying to use this kind of approach to solve a system of linear equations. Now, okay, I should mention here, solution which I refer to as x star of this equation, x equals g x, is called a fixed point, also known as a stationary point of a function g. Okay. So that's where the name stationary iterative method comes from, that the goal is to find a stationary point of some function g that comes from the system ax equals b. Now, what the function g is, that's the devil's in the details on that one. So how are we going to come up with a function g so that if we keep carrying out this kind of substitution, we would end up with the solution to ax equals b? So the way that's done is, for stationary iterative methods, is through what's called a splitting of a. So I go ahead and write a equal to m minus n. Now, there are some choices for m and n. I'll come to those shortly. So if you go ahead and write a equals m minus n, then ax equals b can be written this way. And then from that, we can describe an iteration. So we have xk plus 1 on the left side and xk on the right side. So I could choose initial guess x0, which usually is a 0 vector. I'll make a note of that here. And then I substitute my initial guess over here, and then I solve a system of equations involving m instead of a. And that gives me x1. Then I plug in x1 over here, do this right-hand side vector, and now I solve a system again involving m to get x2, and this cycle keeps going. So now I have a fixed point iteration of this form, xk plus 1 equals g of xk, where this is a function g. So you compute mx plus b, you solve a system involving m. So in other words, it's equivalent to multiplying by m inverse. So this is a function g I have. So instead of solving a system involving a, I'm solving a system involving m. So this gives us some guidance on how to choose m. M must be chosen so that systems involving m are easy to solve, like m is a diagonal matrix or a triangular matrix. It has to be less work than just solving a, otherwise there's no point in what we're doing. Because whatever systems you solve involving m, you're going to be doing that every single iteration, and you might be carrying out a lot of iterations. Okay, so this is the general idea, a framework for stationary iterative methods that so our algorithm just keeps successfully substituting into g, where our function g has this form. So what remains is how do we actually choose m and n so that this actually works. So any questions so far about like just the general setup for an iterative method? Okay. Now, last semester when covering fixed point iteration, we saw that in some cases it would not converge. We have to have some faith that this iteration is going to converge. We just have some criteria on how we split A into M and N so that there will be convergence. So to get an idea of what happens to the error from one iteration to the next, well, I really should wind up these equations here. Well, I'm not going to fix that now. So I'm going to assume that plain old x with no superscript or subscript or anything, x is the exact solution of ax equals b. Okay. So yeah, I have my iterative method as a starting point. So then I multiply both sides by m inverse, just so xk plus 1 is isolated. And then I subtract x from both sides. On the left side, I have the error after k plus 1 iterations. That's one thing that I want. What I really want is a relationship between the error after k plus 1 iterations and the error after k iterations. I want to know, how does the error change from one iteration to the next? Then I can figure out how to get convergence. I want that error to be going to 0. So what I do is over here, okay, distribute the m inverse through. And then I use the fact that I have b here. Well, b is equal to a times x. So here, I replace b with ax. So now I have a. A can be replaced by m minus n. That's how I define m and n. And now a bit of algebra happens. And thankfully some cancellation, because we have an x cancel. And I end up with this relationship in the end. Okay, so xk plus 1 minus x, so the error after k plus 1 iterations is equal to the error after k iterations multiplied by this matrix, m inverse n. So I want to make sure that if I have whatever vector, like my previous error, if I'm multiplying something by m inverse n, I want some kind of guarantee that multiplying by m inverse n will make it smaller. And that'll keep happening iteration after iteration. So if I apply this relationship repeatedly, then this is what I have. That the error after k iterations is equal to the initial error times m inverse n raised to the k power. So this matrix, m inverse n, that I'll label as capital T for convenience, that's called the iteration matrix for whatever method I have. And we'll see a few iteration matrices in just a little bit. So now what I can do is I can take the norm of both sides of this equation, any vector norm, and this is what I get. The norm of the error, using what's called the submultiplicative property of matrix norms that I introduced last time, is less than or equal to norm of t raised to the k power times the initial error. So what this means is, suppose the norm of t is strictly less than 1. So that would actually guarantee that the error goes to 0 as k goes to infinity. So if I could choose a splitting a equals m minus n such that my iteration matrix m inverse n satisfies this condition, I'll have convergence. Now, that condition is a sufficient condition. It is not necessary. So it is possible that t could have a norm equal to 1, in some matrix norm, and still have convergence. So I want to know, is there a condition that is both sufficient and necessary for convergence? And we do have that. So a necessary sufficient condition for convergence on this iteration is that the rho of t, which is called the spectral radius of t, has to be strictly less than 1. Now, I've not mentioned spectral radius before. Here's how we define spectral radius. Spectral radius of a matrix, right here. It's just the maximum, the absolute value of all the eigenvalues of a matrix T. So in other words, if all the eigenvalues of capital T have absolute value less than 1, then so the iteration will converge if and only if that is true. Okay, you know what? I don't know if I mentioned eigenvalues in this class before. Maybe? Oh, I know I mentioned them. It came up with a 2 norm. But I didn't, okay, but an eigenvalues, I think they're covered in Math 326. I think it depends on who the instructor is and who they're involved behind it on. But anyway, in case you need your memory refreshed, this is what it means that an eigenvalue of a matrix. So if you have matrix T times the non-zero vector x is equal to scalar lambda times the same vector x. So in other words, if matrix vector multiplication turns out to be equivalent to scaling for any non-zero vector x, then that x is an eigenvector, and lambda is an eigenvalue. Okay. Now, but we're interested in largest eigenvalues, spectral radius. Now, okay. So it turns out that the spectral radius of T is less than or equal to the norm of T for any natural or induced matrix norm. Like one norm, two norm, infinity norm, any of those. The spectral radius is less than or equal to that. And the reason why is if I have this relationship right here, T times X equals lambda times X, then I can take a norm, a vector norm of both sides. But then on this side, on the left side, I apply the submultiplicative property. It says that the norm of T times X is less than or equal to norm of T times norm of X. So when you get this relationship, if we happen to have the eigenvector that goes to the largest eigenvalue, then we have this, that the spectral radius is less than or equal to the matrix norm. So that gives you the idea as to why having a norm less than 1 is at least sufficient for convergence, since it's not necessary. But this slightly smaller quantity, potentially smaller quantity, spectral radius, that being less than 1 is necessary and sufficient for convergence. One thing that's worth mentioning, okay, well, since almost everyone here has taken math 460 or 560, and therefore you saw fixed point iteration. When I covered fixed point iteration, so just solving x equals g of x, when g is just a function of a single variable. Does anyone remember? I don't know if I was pointing the same question in the math class here, but things tend to be forgotten. But does anyone happen to remember what condition on G would help ensure convergence of fixed point iteration when applied to this? So there's this, it doesn't establish last semester, there's a condition on G that is satisfied to ensure convergence.
Is it absolute value of the derivative valued by Lipschitz constant?
Yeah, and the Lipschitz constant will have to be true of a Lipschitz constant. Not just any Lipschitz constant. That was good though.
Less than 1.
Yes, yeah. The Lipschitz constant has to be less than 1. Okay, so that's connected to what we have here. That the Jacobian, the Jacobian matrix of our iteration function g of x now, Jacobian matrix, that's just the generalization of derivative to functions of several variables. So what that means is Jacobian matrix, in other words, it's dg, derivative of g, with respect to x, is given by t, which is m inverse n. Now to see why, if you look at my definition of G right here, you think of everything as everything here is a vector or matrix, but you think of them as scalars rather than vectors or matrices. You're taking the derivative of this with respect to x. But what do we have here? X is just multiplied by m inverse n. M inverse n itself is a constant matrix. So the derivative is quite simple in this case. So the fact that we want the spectral radius of a norm of the Jacobian matrix to be less than 1. So, whoops. Okay. So this is consistent. So therefore, the conditions that either the norm of t less than 1 or a spectral radius of t less than 1 are consistent with the condition that's the value of g prime of x less or equal to Lipschitz constant less than 1 for fixed point iteration or single variable equation. So either way, whatever the derivative is of your g, you want that to be less than 1. So it's a logical generalization of what you saw last semester in the case of a fixed point iteration for a system of equations. And we're actually going to be visiting that later when we deal with solving systems of ODEs. Okay. Before I get into any specific iterative methods, questions about what we've seen so far in convergence?
Again, for the part where you say that it's consistent with the fixed point iteration condition.
So for a single variable equation, we want this bound on the derivative, or really absolute value derivative. Well, for solving x equals b and using a splitting, this is our derivative. So we want its magnitude also bounded in a similar manner. So the bottom line is, when we're using fixed point iteration for a single equation or a system of equations, you want the derivative of your g, which single variable is just a derivative. For system equations, it's the Jacobian matrix, and in some circles that will also be referred to as the derivative of a matrix. So you want the magnitude of a derivative to be bounded. Yeah.
It's just the notion of, norm, that makes sense.
Yeah.
But that spectral radius, yes.
Yeah.
And looking at it in terms of eigenvalues, like the largest eigenvalue,
Yeah.
as a measure of magnitude.
Oh, okay, yeah. Well, because you think about what's happening with matrix norms, natural or induced matrix norms, it's defined as the norm of A times X divided by the norm of X. In other words, how much is multiplying by A affects the magnitude of the vector. But that's what's happening when you have eigenvalues and eigenvectors. You are, again, so in that case also, you are scaling the vector so its magnitude is increased by the eigenvalue.
Oh yeah, well, again, it's the relationship.
Yeah. Okay. So actually for, if a matrix is symmetric, the 2 norm equals the spectral radius. Any other question? All right, now, finally, after 45 minutes, specific iterative methods. Simplest of all is called the Jacobi method. So describe all the iterative methods that we'll see today. I'm going to break A down into L plus D plus U. So L is the strictly lower triangular parts, everything that's below the main diagonal. And then D is what's on the main diagonal, and then U is what's above the main diagonal. L and U are not the same as from the LU decomposition. So don't even go there. That's correct. It's gone now. Okay, but this is convenient for describing these floating base iterative methods. So for Jacobi method, the matrix M that we have to invert is just a diagonal. So we're solving just a diagonal system, so that's quick and easy. And then N would be everything else. So that would be minus and then L plus U. So this is what the Jacobi method looks like written in a matrix vector form. That you form this right-hand side vector using the off-diagonal parts of A. And then you're solving a diagonal system, but all it means is you're taking this vector and you're dividing by the diagonal entries of A. Now that would require that they're all non-zero. So that's a limitation there. Okay. But this is not how the Jacobi method is normally written. It's actually more informative in this case if we write this out element by element. So what is each element of the new x? Okay, and that's what I have here. So each element of the new iterate xk plus 1 is determined using this formula from using the previous iterate xk. So we're forming this, and then the solving the system involving m part is carried out by just multiplying 1 over AII of the diagonal entries of A. So how you would actually implement the Jacobi method, like in MATLAB, is you choose an initial guess. Depending on the context of your problem, you might already have an initial guess, but if not, you can always fall back on just using the zero vector. So you would have an outer loop that computes each iterate from a previous one. And then you would have an inner loop for computing each component. And within that, you have the third level of the loop right here. And you keep going, your outer loop will continue until you have some convergence criterion met. Like maybe the difference between successive iterates is less than some tolerance. It'd also be a good idea to impose a maximum number of iterations, because one of the iterations diverges. You want to make sure your code stops. Okay, so this is all that's involved in the Jacobi method. That for each iterate, you have a loop that will go over each component of a new iterate, and within that inner loop, you'll apply this formula here. So questions about the Jacobi method? It's not a great method, but it's still used. Next method is closely related, called the Gauss-Seidel method. So I'm going to use a starting point. I'm going to use the Jacobi method again, but this time I'm going to write it out a little differently. Because in this description of the Jacobi method up here, I have a sum over all j not equal to I. So counting all the off-diagonal entries in each row. But now I'm going to break that sum up. Now I have sum over all j less than I, then all j greater than I. Now suppose I compute the components of the new iterate in order. So I goes from 1, 2, up to n in that order. Then what that means is, whatever I is, I've already computed the new components of xk plus 1 for all indices less than I. So what happens is, over here, in this sum, I'm using xj iterate k, but x sub j iterate k plus 1 has already been computed. I'm just not using it. So in other words, this sum uses old information about the solution. So that's something that's easily changed. I can just change this superscript to a k plus 1. So now I'm using the most up-to-date information about the solution that I have available continually. So now I have this iteration that looks almost identical. The only change is right here. For these components, j greater than I haven't computed those components of xk plus 1 yet, so I have to settle for xk. So by making this change, Jacobi method here, change the superscript here, now I have the Gauss-Seidel method. So that's the only difference between them. And so now that in matrix vector form, that would be equivalent to having L multiplied by xk plus 1 rather than xk as it is in the Jacobi method. But now I have xk plus 1 on both sides of the equation. Yeah, but that's okay. Since everything here is linear, I can just rearrange. So that's what I do here. I multiply both sides by d, so I don't have any inverse matrices. And then I take this term involving L xk plus 1 and I move it to the left side. And now I have this. So what happens is, so this is the Jacobi method in matrix vector form. So instead of solving a system involving a diagonal matrix, as in Jacobi, I have a lower triangular matrix here. Now what's weird is, you might think, oh, Jacobi uses a diagonal matrix, that's really quick. Now Gauss-Seidel is using the lower triangular matrix to solve. That's order n squared, this is order n. So you might think, oh, that must take a whole lot more work. But as you can plainly see, Jacobi, Gauss-Seidel, they involve the same amount of work. The reason is that this is doing more work on the matrix vector multiplication side. Some of that is shifted to forward substitution. So it's still the same amount of work, it's just capitalized. Okay. So for some applications, Gauss-Seidel does converge more rapidly, but that's not a blanket statement. You can't claim that all the time. Why is someone calling me? Okay. Also, Jacobi can be parallelized. So there is actually an advantage to intentionally using slightly out-of-date information about the solution. Is that because being able to make this change from Jacobi to Gauss-Seidel is contingent on the assumption that we're actually computing these components sequentially in this order. But Jacobi, these can be always, because we're using null information every time, these can be done in parallel, whereas this can't. So Gauss-Seidel relies on the ordering of the elements. So Jacobi, if you have parallel processing available, if you have many processors, then Jacobi can benefit from that in ways that Gauss-Seidel can't. So there's the trade-off there. Questions about Jacobi versus Gauss-Seidel? But
So, all of these methods rely on, I don't want to say decompositions, because there's no multiplication happening. Like to represent your given matrix as a sum of some matrices.
yeah.
Like how do you come down to those representations?
Oh, I mean, like, you mean like the This? Well, that's really just a notational device that makes it easy to describe the method.
Okay.
And because you don't even need any math to do this.
Yeah.
Yeah.
Oh.
I have one more method. Successive over-relaxation, or customarily abbreviated as SOR. So that is, just as Gauss-Seidel can be thought of as a modification of Jacobi, SOR can be thought of as a modification of Gauss-Seidel. So what I've done here is I've rewritten Gauss-Seidel in a rather strange way, where each component of xk plus 1 is equal to same component of xk plus all this stuff. So I've done like an add subtract thing over here, which I know seems kind of strange. But you can think of this as this is my previous iterate, and this quantity here describes the step I'm taking from xk to xk plus 1. I'm adding this. So what I can do is, what if I still want to go in the direction indicated by this expression here, but maybe I want to change how far I go in that direction. So what I do is, I multiply this whole expression, that's updating xk, by this relaxation parameter that I'll call omega. So I could choose omega less than 1 to not go as far in that direction, or I could choose omega greater than 1 to go even further in that direction. Maybe there's some advantage there. Then I'd like to know, what does this look like in matrix vector form, like I already have for the other methods? So what I've done is I've multiplied both sides by AII, I diagonal entry, and now I have this. And then in matrix vector form, here I'm multiplying by D, here 2 by D, but I'm also multiplying that by scalar 1 minus omega. Then I have all this from those part of square brackets. And now I want to isolate xk plus 1 on one side. So this is the method in matrix vector form, successive over relaxation. Okay, so we're still solving a lower triangular system every iteration. It's just that instead of d plus L, it's d plus omega L. So if omega equals 1, then this is just Gauss-Seidel all over again. But we're mostly interested in applications omega greater than 1. Seems to be advantageous. In fact, in order to have convergence, omega has to be strictly between 0 and 2. Oh. What did I work with this? Oh, okay. Apparently I have a new page thing here. I need to remove that. Okay. The oh, I have a mistake here. Hold on. Oh, no, that's not true. This is correct. Right. So my m inverse n works out to be this. Now, this is a lower triangular matrix that's being inverted. And then this matrix is upper triangular. So suppose I take a determinant of this whole thing. Well, remember, the determinant of a product is a product of determinants. And also, the determinant of a triangular matrix is the product of the diagonal entries. So, for this matrix, I have the diagonal entries of A sitting on a diagonal. So I have AII, but I'm inverting, so I take the reciprocals. And then over here, I have the diagonal entries, which would be 1 minus omega times diagonal entries of A. So I have 1 minus omega times diagonal entries. These diagonal entries cancel out. So I'm left with 1 minus omega raised to the n power, where A is an n by n matrix. But then I point out that the determinant of a matrix is the product of all the eigenvalues. And but the determinant, because product of all the eigenvalues, that's less than or equal to the spectral radius raised to the n power. Like if all of these eigenvalues were equal in magnitude, I would be taking the spectral radius to the n power. Now, what that would mean is this spectral radius, so the determinant is equal to this. The determinant is less than or equal to this. So now I have this relationship. But the spectral radius has to be less than 1. So if I require this expression, 1 minus omega absolute value would be less than 1, I have this condition. Omega has to be between 0 and 2. Actually, it can be shown that if a matrix is A is symmetric, positive, definite, then SOR is guaranteed to converge for any omega between 0 and 2. Okay. Questions about SOR? Now, this is where I get to make all of us feel like we're underachievers. SOR was actually created by a student, David Young, in 1950. His doctoral dissertation was what introduced SOR to the world. So, let's see, we have, well, current or PhD students here. Also, not everybody. Okay, and I want to point out, before class, I had looked up that dissertation. So now, so I want to point out, because this was 1950, this is a reformatted version of the dissertation, where it's all been late typed up. So it's actually readable. But I want to mention in the preface, so it was my advisor, who Gene Gull, who played a role in this modernized version. But I want to point out what had to be done. It's just the preparation of this right here. So originally typed by typists, like on a typewriter, so who's also typing 3 other theses, all of which passed due. Yeah, so David and his wife wrote in all the equations in ink on 3 copies. Okay, and then Dr. Baker retyped it. Okay, and then Barbara Moore. Oh wow, that's my advisor's ex-wife. Okay. I didn't know she was involved in this. Yeah, late text like the current version. Okay. One time I was looking through part of this, and I thought I found a mistake, but I didn't really look into it. So, exactly just to say that. So, it can happen, and people make mistakes in their dissertations all the time. That's embarrassing. to, when I go to the library and look up, old papers, from around that time, and saw how it was done on a typewriter. I think it's really painful to read. Yeah, it seems like the handwritten way. Okay, so, a little bit of history for you. Okay, I think I've come to the end. Of those. So, well, still a little bit of time left, so ever questions about any of this, or homework, or midterm, about board out our skulls? Yes, I'll do it.